Hello, hello. So again, it's that time of the week, but we're in a different setting today. It's not virtual backgrounds. We're not in our usual place, right? What's going on?
Hey, Luca.
Hey, Thomas.
Good to see you.
Yeah, good to see you too. So it happened that, holiday season, not holiday, summer holiday season is approaching, and so we decided that we would spend a few days hacking on around Thunder, but we decided we would do it in person. And since I'm a big fan of Lake Garda, we actually met in Lake Garda. So let me. Hey.
Hey.
Anyway, yeah, we'll be back in our usual locations in a few weeks. Actually, we'll have an episode in New York in 3 weeks. So our August will be a bit nomadic. But yes, so that's great. So I'll look in that direction. You look in this direction, but it's a bit weird. But
Yeah.
we'll make it work. So today is the day where we take a full model, a Llama 3 model, and we run it with PyTorch, regular PyTorch, and we quantize it, and we see the effect of quantization. And we will
Yeah,
talk
that's
a
what we
bit.
promised, right?
Yeah, that's what we promised the last time, but actually I think it turned out fine because we had a lot to show. And so the last time we quantized something that was small, so we could see look at the trace without getting too confused and so on. And today we'll see the effect of that on the full model, Llama 3 model. Um, okay, so why don't you share the screen
Yeah,
and we take a look at the vanilla run with PyTorch Sugar and then we go from there.
yeah, and you will see that it's actually like non-trivial enough that I had to prepare a bit. So I I have my studio here, and I started it ahead of time because this time, and I actually wrote some code too, because this time there will be more going on. Let's import the world, and as Luca promised, we have Llama 3.1.
And what do we use to run it? The
So
Llama model. Is it the Hugging Face transformer?
no, we use libgpt.
Maybe can you show the LGPT homepage? Because I think it's maybe, some of our the people listening here don't know about LGPT. So LGPT is a code base that we started from Nano GPT from Andrej Karpathy the week after the first Llama model was released, and we developed Lit Llama, and then that evolved in something more general. And it's a library with which you can run inference, fine tune, pre-train models, but like 20 large language models. The beauty of this is that there are no layers to it. Again, going back to last week, we were saying like the importance of something being thin, and LGPT is very thin because all the 20 models in here are all in this file model.py, and it's a 400 line file, and they're all in here.
500.
Oh, 500. Yeah, sorry about that. And so you can really see whatever is happening in Mistral, Mixtral, Llama, top to bottom. There's no other dependencies, and of course we depend on Fabric to do some of the training things. But from a modeling perspective, and also the pre-training code, for example, is again 400 lines. The fine-tuning code is 400 lines, and it has kind of very little external dependencies. So it's a great repository to start from and customize, and a lot of researchers and companies are actually doing that. Anyway, back to LGPT.
So that was the advertising
Sorry.
section for LGPT.
Exactly.
But
back to us.
Lucas and I, and my love for doing things like at the very basics, has us having a mouthful of code here. So what's going on is that we first load the model, and it would download it too, and then we grab the config. And So to run an LLM, we need a few things. So if you have these chat models, you need a prompt actually where it says, like, you are a helpful assistant. If you've played with ChatGPT, you know these things, the prompting. Then we need a tokenizer that takes our text to tokens, to integer numbers and back. And then we have the model itself. And today, because we want to show like how we save GPU memory, we will not like start the model on the device immediately, but instead we will start it on the meta device, which is a device, imagine
it's
device.
A fake device, right?
Yeah, it's not a GPU by Meta, but we instantiate our model here.
And sorry, to reiterate, when you instantiate something on the beta device and you have a gigantic model, only the information about how large the parameters are, like the shape of the parameters and their type, are present there, but the actual data, the memory, is not allocated with the weights.
Yeah, and I can show this here. For example, if we see model and then transformer and the embedding. What's the name of the embedding? What do you know?
You need to go into each.
Oh, WT.
Oh, okay. Yeah.
So it's the weight token embedding, no, word token embedding probably. And so if we look at the weight matrix for this would be a fairly large thing. And now this says here, we don't have values because we don't have data, and it's on the meta device. But we see like the size and the detail.
Yep. Which incidentally is what Thunder needs to figure things out, right?
So I put some of the ephemeral buffers on the CUDA device, and so if we look at our memory consumption, we see that there's a little bit taken here, but only I think less than 1 gigabyte or so. And now, because we're going to run eager first, I will materialize the model. And so this goes with model to empty. And then all the buffers and tensors are empty. So I need to rerun this again. And then I will just load the state thing from this checkpoint, which is loading the weights. And if we look at the, no, I should have kept it. So if we look at the embedding weight again, we see that now it has all numbers and it's on the CUDA device. But we also see, if we look here, well, yeah, we spent quite a bit of memory yet already. So we went from 1.4 gigabyte to 20. And that is how large these 8 billion parameter models are. But now we can, we have a model and we can generate. And again, Luca and I, we discussed whether we wanted to show generation, like just a function to generate, because we could do that with Lutivity. It has one of these. But we decided otherwise. So what we do is we take the tokenizer and encode the prompt. So it will be what the llamas eat, and the prompt style will add the "you are a helpful assistant" bit. Then we have the input positions, which is just 0 to whatever the length is of the prompt. And then we run the actual model in inference mode. This gives us probabilities for the next token. And so we sample the token, actually, and this will be a number again. And then we can decode it and print it. And so the first token is kind of special because the prompt goes in. But then the next tokens just get the last generated token with its position, and then we continue from there. And so we can run this, and as you might expect, this gives us here the tokens. And we see.
Of course, in LGPT we have like higher level APIs to do all this behind the scenes. But this is one level down, and so
yeah,
we have a bit more visibility on what's going on behind the scenes, how the sausage is made.
Right, and obviously it's neat that you can do this easily. But to get a bit more of a feeling, like if we're getting 20 some tokens per second, we're spending about 15 milliseconds per token. And so we can use the torch profile again to get a feeling of what's going on. And for this, I have adapted the sprint device time function to use actually self device time total. And so let's run the profiler on one token, and let's print the device times here. Oh, this worked really well. Yeah, so I thought I'd spare you like the vast output by cutting it short, and then it got more confusing. So here's the main spend we have in terms of kernels. So we have here A10 matmul, which is
what is A10? What is A10?
So A10 is the underlying default compute backend for PyTorch. So this is the PyTorch matmul, if you will. And then we see there's a specialized kernel for matmul, which you can see here, the GEM, which stands for General Matrix Multiplication, I guess, or General Matrix Multiplication. And then there's attention kernels. Here's efficient attention forward. And then here's a cutless kernel. And if you look at it, it's a memory efficient attention kernel. And then there's some more kernels. Here's a matrix times vector kernel. But we see that basically here are our 50 some milliseconds. It looks it looks a bit slower here in the profiling than it was up here.
Yeah.
I'm not entirely sure what's going on. But so this is how the eager model runs. And we will see, and again, I want to point out that we have used a lot of memory, and we will contrast that with quantization later. But first, let's maybe talk a bit about how the quantization works under the hood.
Yeah, as a transform, right? So we just saw that, and we touched upon it the last few times. Essentially, what happens there is that not necessarily the matrix multiplications, which are the most most expensive operations, as we saw, that the model runs. We could either sit down and try to further optimize the way the matrix multiplication is run. But actually, the problem we're bumping into in this case is not really that the kernel is slow, is badly implemented, right? It's another problem that we mentioned, which is while running this multiplication, we also need to move data, and if the data that we move cannot move fast enough, then our kernel will take more time to execute. And so that is the culprit of the slowness, or at least that's our hypothesis.
And so the solution, obviously, then is to move less data.
Exactly.
And when you're quantizing from 16-bit, which is the default compute here, to 4-bit, you are saving like 4x on the size of the weight memory.
Yeah. So if you have a pipe here that goes from here to there, there is the compute, and here is where the data resides. Instead of in 16 bits, instead of moving all these bits here, you can quantize them and move only the subset of the bit, or well, it's not a quarter of the matrix, of course. It's every single entry of the matrix will be represented by fewer bits. But anyway, if you then compact them on the upper left, you will have like less volume of bits to move, And since these things like, where were you running the thing on L4?
No, A10G.
A10G. So the A10G, if I'm not wrong, has 600 gigabyte per second of, that this pipe can move. And so if you have many gigabytes to move for your matmults at the same time, at a given time, or less than several megabytes to move at a time, this will take time. And so the cores will not happy, will be waiting for stuff to do. Okay, so that's good. And now we get into how we can turn the a model that we saw, a LibGPT model, LibGPT implementation of a Llama 3 model, and how can we turn it into something that will make this trick move, this data move faster. So we apply a transform through Thunder. One of the ways, of course, you can also monkey patch your model. You can go and change the implementation. But at Thunder, we want to acquire the model again, have all the instructions one of the other, take this trace and turn it into another trace that represents the computation with some transformation. And this process, we call it transform, can add data, can add operations, can replace operations with other operations, and so on. And so today, what we're going to do is we are looking at how this transformation happens, when it happens, and what effects it has. So we have a few minutes. We'll go super fast. So the first thing that happens when you call thunder.jit on your model, right?
Yeah.
A few things happen right now, and a few things happen after when we actually call the model with some data, right?
Yeah.
First thing.
So one thing to remember about PyTorch itself is that it has essentially two parts, a model. You have the container part where all the weights are gathered, and then you have the computation itself. So that was one of the success things about PyTorch, that this really stuck the object-oriented API that supplements a functional API. And so if you look at that, these need different treatment, and so that's what the JIT does. And so first, when you JIT it.
Okay, so this is where the computation happens.
Right.
And this is where we create the state of the module with all the parameters, the buffers, and the global state that it has. And so first thing when you JIT it, the first thing that happens is that the module becomes a Thunder module. So the Thunder module is an object that will behave kind of the same. It will have the same parameters and the same properties, but will have additional properties attached to it. When we want to transform a module into something else, for example, when you want to quantize, quantization works by saying, okay, I have a 16-bit word or parameter, and then I want to turn it into a 4-bit parameter, which is shorter, fewer bits, but also it needs a few other numbers, a few other buffers to keep track of, for example, what is the scale of that shorter number. How you can convert back to a 16-bit with a certain level of accuracy depends on those 4 bits, and also some global information that can be global at different levels. So you need more buffers to store in the Thunder module. So if you transform a Thunder module into another Thunder module, in this case, right, you will have a Thunder module that has been acquired from the module, and then you have a quantized Thunder module that goes through the quantization transform. So the first type of transformations that we have is the one that turns a Thunder module into another module that has the extra stuff that is needed for the thing to happen.
So I would probably say the first thing that our transformations do. So it's one type of transformation, and there's various things that they do. And one thing is they transform the module.
Yeah.
And they do so when you JIT the model, like that's immediately.
Yeah.
And that is in contrast to the computation, which also needs adaptive, right?
Yep. So the computation, when we acquire the computation, well, first of all, when is it transformed? Well, sorry, this is very bad. Module, okay. Model, sorry, J model, the JITted model, let's say. So when I say J model X, and I call the forward of this function, this is where Thunder understands that with certain inputs, the code will kind of flow in a certain way, and you can keep track of what happens to the inputs and what happens to the general. You remember we talked about it. We take the bytecode, Python bytecode, and we trace the computation with a special interpreter, which is not C Python, but it's a Python interpreter written in Python that is inside the interpreter.py in Thunder core. And that allows us to understand what happens to the tensors without actually performing the computation. So we fake the computation so that we can build this thing here, the trace. And so we know what happens to the inputs and what operations are called. And but this forward is basically broken into three things. The first is a prologue, then the computation,
which is the main part if you want to stick with the prologue,
and then the epilogue. So the prologue, what does the prologue do?
Well, yeah, the prologue has two things that it does. So one thing is we're JITting it, we're only running it when we get the inputs from the user, and the user tries to run the Thunder module because we want to make sure that we know about all the information we have about what's going on in the computation. And part of that is, for example, the shapes of the inputs. And so what the prologue does is it checks whether the inputs match what the computation needs. And so we have a caching mechanism here in Thunder. If we have seen the shapes of inputs and d-types and devices, etc., before, then we can reuse the computation trace. And so this checking whether a given triple of traces here applies, this is part of what the prologue does. And the other thing is that it links the module part, like the storing of the weights, to the computation part. And in PyTorch, normally this is interleaved because all the forward functions, they will access self.weight or whatever. But so for us, we want the computation to be really functional. That means that it wants all the weights as inputs. And so the prologue, the second task of the prologue is to gather all the parameters and things that the computation needs and feed them or return them to feed them into the computation as arguments.
Yeah, and we talked about those scaling factors, right, that quantization needs, the buffers there. Well, those will have to be fed into the new computation after the transform. So we have a pre-quantization computation trace with some arguments. The transform will create a new computation trace with extra arguments that represent the scaling factor for the weights that we introduce the moment we quantize it. And so there's no magic, there are no hiding things in objects. Everything is very explicit, but it allows us to then go in and optimize things further and make them composable, because now we can reason about something. The world is known to us here, the complete world, including do we access a global variable and so on. It's all captured in the inputs of the computation. It's all very explicit. And then the epilogue is going back to module world.
If you have things to update, like with the LLMs, you have this KV cache of the previous tokens that the model has seen in the computation for a given prompt. So this updating that happens in the epilogue. But for now, you can forget about the epilogue. The key thing is the prologue checks whether the cache entry is the right one for the computation, and it grabs all the parameters. And so the transformations, they have to update both the prologue and the computation, because the prologue needs to get the extra parameters. It needs to update the checks from the unquantized weights to the quantized weights, because suddenly they're like an integer quantity, an integer tensor with a different shape. And also, then the computation needs to be updated, because it needs to take these additional parameters and then also replace the computation, that's the non-quantized matrix multiplication, with the quantized matrix multiplication.
Yeah.
And so one of the guiding principles is, and Luca mentioned composition, that we want to be able to compose it. And so one of the guiding principles we have here at Thunder is that after the transformation, the world should look exactly as if you fed that already into Thunder. So after the quantization transformation, we want the model to look like you could have quantized it manually and then jittered it through Thunder. And that enables us to do the composition, that we always have a state as if you had the initial Thunder model.
Perfect. Okay, we went through everything. So basically what happened is that we implemented the quantization transform using these primitives. And we have a transform class if you want to look into it, which is the mother class of everything. And it implements different hooks. And those hooks are the various transformations that you can make. So you can make a transformation that transforms prologue, computation, and epilogue. Or you can make a transformation that transforms the state dict. So, and we haven't talked about that, but we'll talk about that in the future. But essentially, if you load data from a checkpoint, but you had to load it inside a model that has been transformed, then you need some transformation to happen to your state dict, right? So you can express this in this transform class, which is nice because this encapsulates the whole life cycle of a transformation. And so it also becomes a package that I can apply to a model and that I can compose with other transformations, but it's all self-contained.
Now you're getting into the theory, but let's go back to the code, right?
We go back to the code. Like stop sharing here and share there.
We'll share here. And obviously, it's not like that far apart, but yeah.
I'll throw it on you.
Right. And so here we are with our code again, and I need to switch the window. And so what I did here is I replaced the thing where I manually materialize the model with a thing that does that jitters it. So nothing happens here yet in these things. That's just set up. I'm getting the quantization transform. I'm also getting the static here with a lazy loading in order to not load the entire thing at once. And in addition to the quantization transform, because we started on the meta device, I also added the materialization transform, and that will, after it has materialized the model or during the materialization, well, actually after. But so after it has materialized the model, it will load the state dict. And so...
so just to play it back, this means that up until that point, we've operated in meta.
Right. All parameters were
so I could even do it on my laptop if I wanted. almost maybe because of the ephemeral buffers, but and I could have a gigantic model up until that point, and I would still be able to transform it.
Yeah. So, and then after we did the model in Thunder, and I've prepared that because the initial tracing is a bit not that fast, and we don't want to bore you Friday 5 p.m. or 5:30 now. And so we can run this now again, and we see that it generates the code again, and we also see that we've seen like a easy 25% speed up here from the quantization. And so we can also like look at, we were at 20 before, now we're at 25-ish. We can also, again, look at what happened to the kernels. And what we actually see is that the kernel times, remember that the matmul had 30-some milliseconds, so we have 1/3 of that. The attention is relatively similar. And then there's nvfuser pointwise ones. Remember that I cut off everything that is below 1 millisecond, so these probably are individual operations. You see here that there's some things going on. So we have all the other optimizations like nvfuser, which produces optimized kernels, in here in addition. So we see, well, the GEMS got very much faster. The other thing that we see is that we're now operating the same thing with just a little over 10 gigabytes. So it's 10.6 gigabytes here. And that has the quantized model weights, which come in around 6 gigabytes. And then there's 4 or 5 gigabytes for the key value cache, which we, again, in another transformation could then quantize as well. But so this is going on. The other thing we're seeing is that we get from 50 to 40 milliseconds per token. So that's not in line with the quantization, with the speed up in the kernels. But what we see here is that our maximum GPU utilization was about 67%. And so one of the tricks we will have to play in further episodes will be to get that further up. But so here we have a speed up with quantization. This has been the simplest case for your and our benefit. And this is what I wanted to show you here.
Yeah, that's great. Can we say, like, the kernels that PyTorch ran were not slow, right? And potentially the 4-bit kernel was not particularly optimal. The thing is that the movement of the data got faster because there was less data to move. But this means also that that kernel, the 4-bit kernel, just to clarify, doesn't compute in 4 bits. It still computes in 16 bits, but it accepts the weights in 4 bits. And then within the kernel, it turns it into numbers, it restores the precision to whatever it's needed to perform the computation. So the computation still happens at full precision, but the important thing is that the weights that are brought to the computation are in 4-bit.
Yeah.
So it's very fascinating. Well, we got speedups. Of course, there's a lot more speedup that one could have, and we'll show them in the future. But the immediate thing that we wanted to demonstrate is there. And yeah, I think we're good. Anything else you want to add?
No, I think you have a good weekend, everyone, and we'll probably hit the lake pretty soon.
Yes, exactly. Okay.
See ya.
Bye-bye. Thank you.